So now let's talk about the matrix representation of a linear map itself. Okay, so we've got a linear map, and this theorem tells you that a linear map is entirely defined by the image of a basis of A. Okay, so maybe we probably even said that already. So try to do the proof. It's so as we see, it's very similar to the theorem, this one, that if you've got a basis of E, then the image of a linear map that is acting on E is going to be spanned by the image of the basis vectors. Okay, so it's very, very similar. So try to prove this theorem. Okay, the map is entirely defined by the image of the basis of A. So you've got a hint to help you, this one, okay? So assume you've got a basis that is composed of, well, let's say P vectors. So that means that any item U in E can be written as a linear combination of those basis items. This is exactly what is written here, okay? And then what is F of U? Okay, so pause for a while and try to write it using the linearity of F. Pause the video and write what it gives you, and so that you understand why this is entirely defined by the image of the elements of the basis. Okay, so what did we have? We had that U belong to E, so U could be written as linear combination. So we said we had P elements. We had P elements. So from 1 to P of coordinates lambda I EI. Okay, that's how we can express U. So that when I want to apply F, my linear map to vector U, it's the same thing as F of the sum of lambda I EI. Okay, and using linearity, it just comes very naturally that this is going to be, well, the linear combination of the images. So sum from 1 to P of lambda I F of EI. Okay, the lambda I, they belong to R. They are just the coordinates of U in this basis, and F of EI are just the images of the basis elements. So if I know the basis elements F of the image of the basis elements F of EI, I know the image of any element U in E. Okay, so that is why we can say that a map is entirely defined by the image of the basis of a basis of its domain. All right, so that was the theorem 22. All right, so that's what we found just at the previous slide. So what comes next? As vectors F of EI belong to F, they can themselves be written as linear combination of basis of the basis B prime of F. Okay, all right, and so we can define the matrix representation of so we can define the matrix representation of a linear map. Okay, so what do we have? We have a linear map F that goes from domain E to domain F. Domain E has basis B, E1 up to EP, so dimension P. Domain F doesn't have to have the same dimension, so we go F1 up to Fn, that are going to be the elements of the basis B prime of the codomain. And so if I want to determine entirely my map F, I have to know the image F of EI, okay, for I equals 1 to P. And as F of EI belong to the codomain, to F, they can be expressed themselves, well, they will be expressed naturally themselves as linear combinations of the basis items of the codomain. All right, so here I put in each column the coordinates of f of ei in the matrix of the codomain. Okay, so I can build a matrix that has in each of its column the images of each of its vectors. Okay, of each of the vectors of the basis of the domain. Okay, so now we can treat the following example. So we've got a map phi, which is defined from R2 of x with the, as its domain and codomain also R2 of x, the meaning so polynomials of degree at most 2, and it takes a polynomial p of degree at most 2 and associates the polynomial given by x times p prime minus p. Okay, and the question is find the representing matrix of phi in the standard basis of R2 of x. Okay, so just before you do that, maybe we could imagine some preliminary questions. Some preliminary questions could be prove that the map is linear. So it's always a good exercise for you to try it. Another interesting question, prove that indeed the image of this map when the domain is R2 of x is a sub a subspace of R2 of x. Okay, that would be another interesting question. All right, and also naturally all the questions we treated last time about the kernel and the image, the injectivity and the surjectivity of a map, but the very important and excellent result that we're going to see during that lesson is that actually that now that you have a matrix representation of your map, anything you can infer on the matrix itself relates exactly directly to the map itself and vice versa. Okay, so I think you should now pause the video and try to find the representing the representing matrix of this map phi. So just a few hints if you need a bit of help for that. So we said we were going to use the standard basis of R2 of x, which is, well, this one here. Okay, so the one given by polynomials 1x and x squared. And so we said the matrix was given by the columns of the matrix were representing the images of the basis vectors. So you have to look for the images of the basis elements. So you have to calculate phi of 1, phi of x2. So how did it go? Okay, so let's do that. Phi of 1. Phi of 1 is going to be x times p prime is going to be 0 if p is equal to 1. Of course, its derivative is 0 minus x minus p, so minus 1. So phi of 1 is negative 1. Is the constant polynomial equal to negative 1? Phi of x is equal to x times p prime is 1 minus x. So actually it's going to be the 0 polynomial. And phi of x2, it's going to be, so x times 2x, which is the derivative of x squared minus x2. So 2x squared minus x squared is just x squared. Okay, now you have to write these as vectors expressed in the basis of the codomain. So the basis of the codomain is also the standard basis of R2 of x. So negative 1 is actually going to be, well, negative 1 times 1 plus 0 times x plus 0 times x2. The polynomial, the null polynomial, is of course going to be represented by the 0 vector, and the polynomial given by x square is going to be represented by the vector 0 times 1 plus 0 times x plus 1 times x2. Okay, so these vectors show the component in the standard basis. The standard basis is 1, x, x2. These corresponds, of course, to the coefficients in front of 1x and x2 of each of those, all right? So now that we have those three vectors, we can just concatenate them, and this is going to give us, okay, that's the three vectors we obtained. This is the ones we've just calculated before, and we put them together in the matrix. Okay, that's the matrix that is going to represent our map phi from R2 of x to R2 of x. Okay, so you see here we've got a square matrix because, well, actually the domain and the codomain are the same, and so we've got a square matrix, but we could really, depending on the dimensions of each of domain and codomain, we can have any form of matrix as long as we have finite dimensional spaces. Okay, so one of the uses of this is that this proposition is quite nice. The image of a vector. So you've got a map F that belongs to the set of linear map between E and the vector space E and vector space F, which are both have finite dimension and two bases, corresponding basis B for E, corresponding basis B prime for F. And so you know that you can make the matrix just the same way as we did before of the map of the linear map F by writing in columns the image of the elements of B expressed with respect to basis B prime. Similarly, we saw that at the beginning of the class that for any x in the domain E, we could represent it by a matrix, by a vector, let's call it big X, okay? And actually, if you want a vector representation of the image of X by the map F, it's just going to be given by the multiplication of the matrix of F times the vector of X. Okay, isn't that nice? All right, let's go directly to oh no, maybe we can read that quickly. If F is a linear map from vector space E to vector space F, so it's just rereading of each of the points. So everything I've said. E has a basis denoted B, F has a basis denoted B prime. We have small x in E, it has a vector representation big X, okay, in the basis B. M, the matrix representation of the map, and very naturally you can calculate the matrix vector multiplication. So if you write all the details of this matrix vector multiplication, you will see that it corresponds exactly it will correspond exactly to what we're looking for. Why? Because you know that if x, well, you can write it this way. If x is actually a vector, let's call that x1, x2, xp, okay, in the basis B, it means that it's x is actually x1 times e1 plus x2 times e2 plus xp times ep, and so f of x is just going to be x1 f of e1, etc., plus xp f of ep, and each of these, okay, that corresponds to one of the columns of the matrix of the map. So that's exactly the matrix multiplication m times x. Okay, and so that's just a writing of this matrix vector multiplication. So next, read that back to our map phi with the matrix representation we have found. Find the image by phi of this polynomial. Okay, so what do you need to do?